Okay, so we have topic 3, Laplace transform. This is basic, not that deep for our first year students, mathematics 1B, undergraduate. So the first thing we are going to determine the Laplace transform of the common functions that we will apply to part C. So the first thing, we are going to get the Laplace transform of a constant, and then goes to this and this. All right. So let's begin. So a Laplace transform, okay, a Laplace transform of f of t is defined by f of s. So it transforms a function of time to a function of complex variable. Now this is found by the integral 0 to infinity f of t, our function, times e st dt. Good. Now we have that. So once we have this, we can substitute our f of t, which is 1. So we are integrating from 0 to infinity 1 dot e st, then dt. Remember, we are integrating f of t times e minus st, and f of t is 1. So we just put it there. Now this is simply the same as integrating from 0 to infinity e negative e st and dt. Now we know that the standard integration of e power at, okay, let me not use a because we have already used that. So the standard integral of EUT using integration by substitution, so that we don't go through that. Maybe we'll cover that in another part, I think mathematical physics, which is not in this class, that is year 2. So when you want to integrate EUT with respect to time, then the standard integral is EUT divided by the coefficient of t, which is u plus c. This one can be proved using integration by substitution. I don't want to do that now. Now we are going to apply the same here, so that we are going to have 0. We are going to have our integral will be e minus st divided by s, because x is divided by negative s, because that is what is in front of t, then plus c, and then we are integrating from 0 to infinity. Now, we substitute the higher bound, we get e negative s times infinity, which is our time, over negative s plus c. Then this, we are subtracting the lower bound, where we now substitute 0. So e power 0, because 0 times s will become 0, over negative s plus c. So you can see this will cancel that. And again, there's some mathematical concepts you need to understand. Let me just circle this here. You can confirm that later. Now, there's something you should know, that as t tend to infinity, the exponential part, the power of the exponential become very large negative. And for that case, this particular function vanish. So as t tend to infinity, e power negative s t will vanish, will be 0. That is it. E power largest negative is just 0. So on the other hand, we know that e power 0 is 1. Any number raised by 0 is 1. So once we have that, we can continue and say our answer here is 1. Okay, we now need to subtract and get the answer. So we have 0 for the first part here. As t tends to infinity, this term vanished. So 0 over negative s is 0. So 0 minus the lower bound, which is 1 over negative s. Now this becomes 1 over s. So our Laplace transform, which is f of s, for 1 is 1 over s. So remember that. And if you say 2, it is 2 over s. For 3, 3 over s. For 4, 4 over s. So it is standard. Now we move on. The next part, we want to derive the Laplace transform of an exponential function. Again, this is common, so once we find one, we can apply it to a similar equation. Okay, so we now go very fast. So we are going to do the Laplace transform of f of t, which is our f of s, will be integral from 0 to infinity. Our f of t is e power negative at, and then times e power negative st, which is there in the definition of a Laplace transform. You see it is f of t e minus st, so that is here. And our f of t now is e power negative at, then dt. Now we need to work out this part of the exponential. So we know that e power negative at times e power negative st. Since these are exponential, we apply the index law. So we add the powers. So e power negative at plus negative st. So we can have e power t negative st, I just alternate, then minus at. The reason is I started with this, then followed with this, because we are interested with the s here. Now when you factorize, it becomes e power negative into bracket s plus a, then t. So our function that is outside, the function next to t, the coefficient of t is negative s plus a, because we need it for following the standard integral of e here. Good. Now we proceed, and we are going to have integrating from 0 to infinity our e minus into s plus a t, then dt. Now again, because we already know our coefficient of t is negative into s plus a, we apply this. Integrating e power ut is the same as eut over u plus c. So our u is a negative into s plus a. So we are going to have e power negative into s plus a, all divided by our t here, all divided by the coefficient of t, which is this. So our u is all this. So negative s plus a. Then this is plus c, integrating from 0 to infinity. Hope that is fine. Now we continue substituting in the higher bound. What do we have? We have e and negative s plus a into infinity, because our t is infinity, negative s plus a, then plus c, minus, what do we have? At the lower bound, t is 0, so the entire power here will be 0, divided by negative into s plus a, and then plus c. So automatically c goes because of the subtraction. And you know very well that this will become 1 over negative into s plus a, because what happened is e power 0, any number raised power 0 is 1. Now on the other part, remember what we said, as t tend to infinity, this power become very large negative, and e raised power very large negative is simply 0. So it means the first term here vanish, so that we have 0 minus here. Now when we do that job, we have negative, negative, positive, so 1 over s plus a. So our Laplace transform f of s for our function f of t is 1 over s plus a. Now that is important for you because it's standard. We can apply it to where exponential functions are involved. Now we have another case where it is positive. Already I know the answer to this. It is just going to be s minus a because this is positive. So we don't need to do this. So for your practice, confirm if Laplace transform of f of t, which is equals to f of s, integrating from 0 to infinity, our f of t is now e power at, this is positive, times e power st. Remember this is negative. Dt is the same as 1 over s minus a. Now that I know how we deal with exponential, if it is negative, like what we did here on top, it was negative 80, I got 1 over s plus a. I expect e 80 to be 1 over s minus a instead of plus. So this is our assignment. Please confirm this and you can write your comment on the comment section if you can show this. So I will not show this because it is simply the same step here, but we only need to make sure we avoid negative for this, our f of t, because it is positive. So since I know that ft e power negative at is 1 over s plus a, then automatically e at times e negative st will be 1 over s minus a for you. You can confirm that. Now we move on to the trigonometry, the Laplace transform of a trigonometric function. Good, and we start with sine. So you'll work out that, and I think you will be okay. I don't think that will be difficult for you. So for us to work out this, we remember Euler formula in complex numbers. That is the first thing. So the first thing, recall e power a I a t. Remember, our function here is at. So remember, Euler formula e power I at is the same as cos. If you remember, it is the same as cos at plus I sine at. Hope we did complex numbers in topic 2. The Euler formula for e I at is this. This comes from e I theta, which is given by cos theta plus I sine theta. So it's the same thing I've applied. Our theta is 80. So this is what you should recall in Euler. I hope this is fine. So we want Laplace transform of sine 80. Sine 80. So we are not going to do cos 80. But of course, we can do it at all, or we can do cos 80. Oh, we have cos 80 in Roman 2. So we are going to deal with sine 80. So we have to go for sine 80. Now sine 80 in exponential form is e I at minus e negative I at divided by 2i. That's the definition of sine 80 in exponential form. So we are going to apply the Laplace to this. So we can rewrite this as 1 over 2i into e I at minus e negative I at. Now this is what we are going to do. Now we are going to find the Laplace transform of sine at, and we can now express it as integral. Of course, 1 over I is constant, so let it comes out. So we can express it as 1 over 2I integral from 0 to infinity. Our f of t, which is our sine at, now we know is e into bracket ei at minus ei negative I at, close the bracket, times e minus st, then dt. So this is what we want to work on. Good. Now we can split this into two. We can work on the first case and the second case. Because Laplace are linear, we can use linearity theorem to solve that particular problem. So let's do that. So the first case, we are going to work on the first part, which is the positive. Then we work on the second part. So let me do that. So 0 to infinity, the first case is ei at dot e minus st. Then the other case, we are going to use integration from 0 to infinity e minus I at, then dot e minus st. We have two parts. So this times this and this times this. So the first case, we are working on this times this, which is this. And then the second case, this times this, which is this. And remember, the negative is in between. Because Laplace is linear, so that can be done. Now combine this. So if you combine 0 to infinity using index law, so we'll have e power I at plus negative st dt. I will have dt here, I forgot that, and dt here. Now we can have 0 to infinity e. What is common here? Let's see. We need to rearrange, so we'll have st negative, then plus I a t dt. Now this is equals to integrating from 0 to infinity e. Now common is t, so it is negative into s minus I a, and then t. So I've just factorize negative. Negative times s times t is negative st. Negative times negative ia is positive ia. Then t times ia is t. So this is what I've done. Just factorize to get that. Now integrating this, we now know it will be e minus into bracket s minus ia t divided by the coefficient of t, which is the whole thing outside. So negative s minus I a, and then plus c. Then we are integrating. This from 0 to infinity. Now we are good with this. Because when you substitute infinity, the term vanish. So we don't need to repeat that. So when you substitute the higher term, it is 0. When you substitute the higher term, is it 0? Then minus, so 0 plus c. This is when you substitute the higher term. We already did that. Then minus, when you substitute the lower term, it is e power 0 divided by negative into s minus I a. Correct. Now c cancels, so this is plus c. C cancel c, and now negative become positive. So the value here is the Laplace transform for this part will be 1 over s minus I a. Of course, we can predict the other one if you don't want to go through the whole process. So what will be the other one if you predict? think we just move that. So we can predict the other one anyway. So this one was for positive. For the negative, it will be a plus. Yeah. So if you work out this, you will expect to get 1 over s plus ia. Yes, when you work out this, the Laplace transform will be the same as this. Now for positive, we got 1 minus is minus ia. For positive, when you work out this, you should get this. I don't know whether it brings problem, but I can show you that. But we did that. The Laplace for the positive exponential is 1 is s plus a. So we don't need to repeat that. So our answer is 1 over s plus ia. Now bring them together. You now have 1 over 2i, remember that, into 1 over s minus ia, then minus 1 over s plus ia for the other one. Now you can continue to work out this part. The LCM is the product, that is s minus ia times s plus ia. Now the negative goes here, the positive one. So s plus ia, okay, then minus. The positive goes here, the negative one. So it is s minus ia. Remember, the whole thing is multiplied by 1 over 2i. So we'll now have 1 over 2i into, we can collect the like terms. So we'll have s minus s. S minus s, and then plus ia plus ia. This is ia negative, negative, positive. Divide hereby. This is a complex conjugate, multiplying complex number with its conjugate. You just square x and y. So this is just s squared plus a squared. I hope you remember that from complex numbers. You just square the s and then square here. When you square here, I squared is negative 1. Negative 1 times negative is positive, then a squared. Now what do we have? This cancels, and we have something nice for sine at. So we'll have 1 over, so we have 2i. So we'll have 1 over 2i into 2ia, because we are adding ia plus ia is 2ia, divided by a squared plus a squared. Now this cancels at that. So the answer for our function, the Laplace transform of sine at, which we were asked, is simply f of s, which is just a over s squared plus a squared. Long journey, but we have it. That is also standard. You must make sure you remember this so that we don't need to derive them when we will apply them. Now we go to the last one, so that we'll now have our complete table with the others that we'll just add. We don't need to derive everything. Now from our expansion of the Euler here, where did we start? From here, we have done the imaginary part. So we can also do the same for this. So cos at, we need to write that in standard form. So we need to write cos at in Euler form. Now in exponential form, cos at will be e I at plus e negative I at all divided by 2. So this can be 1 over 2 into e I at plus e negative I at. The good thing, we have already done this and this, so we just need to record. Now, the Laplace transform of E I, okay, let me just put it. The Laplace transform of 0 to infinity of E I at dot E negative st dt, we already did that, and we can quickly do that. We have done it somewhere here. Here is just 1 over s minus I at. So it's simply 1 over s minus I a. Similarly, the Laplace transform of E, the negative part, E minus I at dot E minus st dt can also be done. We already did that, is s plus I a. Here we have it, s plus I a. Now combine them back. So our combined Laplace is 1 over 2 times 1 over s minus ai, that is what we have, then plus 1 over s plus ia, because we had a plus in between the exponential. This is the plus. Now work this out by 1 over 2. LCM is s minus ia times s plus ia. Now the negative goes the positive time, so it's s plus ia. Then plus the positive goes the negative time, so it is s minus ia. And then we close here. So when we do that, you're going to have 1 over 2 into s plus s plus ia minus ia, all divided by, for multiplying a complex number and its conjugates, we simply have s squared plus a squared. That is another thing we applied from topic 2. Now this will be 1 over 2 multiplied by 2s over s squared plus a squared. The reason is this will cancel this. And again, you know, this cancels that. So the Laplace transform of cos at is equals to f of s, which is s divided by s squared plus a squared. Very important derivations that we will apply. So this one is very important, very important. And I also circle this. Where's the other one? For sin 80, did we do that? Yes, sin 80. So this is also very important. These are standard Laplace that once you know, it's very easy to work with the Laplace transforms. And then we also need this. This is very important, even if it is not done, but we borrow it from what we did on an exponential. So you need to remember, if you are dealing with the positive exponential, it is 1 over s minus a. And when you are dealing with a negative exponential, it's 1 over s plus a. And then for a constant, it is just 1 over s. So if it is 3, 3 over s. If it is 4, 4 over s, like that. And that is that. Now, let's have our table, because it is good to have the table before we proceed. Now, our table reads, Laplace transform of 1 is 1 over s. Now, Laplace transform of e at is 1 over s minus a. Laplace transform of e minus at is 1 over s plus a. They are moving. And Laplace transform of sine at, we have already derived that, is a over s squared plus a squared. Can confirm that because there's a over a squared plus a squared. And then the Laplace transform of cos at, we have already derived that, is s over a squared minus a squared. Now we are adding 1, which we didn't derive. The Laplace transform of t power n function is n factorial divided by s power n plus 1. And another one we didn't derive, which is first shifting theorem. The Laplace transform of e bt multiplied by our function f of t is simply f s minus b. We shift our Laplace transform by b because of multiplying our function of time with ebt. So these are all what you need for now for the basic Laplace transform. These ones. Good. So it's now time to do easy work. Once you have everything, easy work. Now we have something here. We have this part here, which means it looks like E at multiplied by f of t, because this is et multiplied by another function, which is first shifting theorem, which says f into s minus b. Let me change a here to be b. Now the first thing, let's get the Laplace transform of sine 3t, applying what we have learned. Now from what we have learned, okay, let me recall that for you by saying at is the same as a, you remember, over a squared plus a squared. Now if you have sine 3t, our a is 3. Good. So we are going to have the answer as a, no, now not a, because we know a. So the answer will be 3 over a squared plus 3 squared, which is 3 over a squared plus 9. Good. Now you see how it is easy once you know the standard. So Laplace of sine 8 is a over a squared plus a squared. Now we have it here. But we are shifting by b is t, because we have e power 2t. So there's something we have e power 2t. So from here, our b is equals to 2. So that means we are shifting s minus b, so it will be minus 2. From first shifting theorem, f, we are shifting by s minus b, and our b is 2. So now we bring here, we shift s here. So our Laplace transform, when you combine e 2t dot s, our sine 3t, will now be f of s, which is our answer, will now be our shift. It means we shift s here by 2. So it will be 3 all divided by s minus 2, which is our b, squared, then plus 9. So that is how easy it is when you know the standard Laplace transform, which we have just listed here after deriving 1, 2, 3, 4, 5. I've only not derived 2, which you can try yourself. Now we go to the next one. It becomes very simple if you master. Now let's go. Now we want 4t. And now we want a Laplace transform of 4t. Now first 4 come out, so Laplace transform of t. Now we know that we now recall that Laplace transform of t power n is n factorial divided by s n plus 1. You have it here, this one. So our n from this is 1 because t is power 1. So our n is equals to 1. So we'll have 4 times Laplace of Tn is 1, so it is 1 factorial divided by s 1 plus 1, because our power of t is that, which will simply be 4 over s squared. Look how simple is it. Now we move on to the next part. The next part is 2e4t. Now this relates to 2 times e at. Okay, now we can recall again the Laplace transform of e at is simply 1 over s minus a. So it means we are going to look for 2 into the Laplace transform. Okay, we have already said that. So it will be 2 times the Laplace transform of, okay, what is our a? We need to go slow. Our a is 4. So remember, our a is equals to 4. So it means we are going to have 2, which is our constant, times the Laplace transform of e at with the 1, which is 1 over s minus a. But now it will be 1 over s minus a. Our a is 4. You can see a is 4 here. Now this is just 2 over s minus 4. Now, our answer, which is the Laplace transform you are asked, is simply the first case, which is 4 over s squared, plus the second case, which is 2 over s minus 4. That is done as well. So that's how easy it is if you master the table. Now the last part, we have, we have the Laplace of 5 cos 2t, then minus 4t cubed. So this we can rewrite as 5 times the Laplace transform of cos 2t, because 5 is a constant, minus 4 times, 4 is also constant, 4 times the Laplace, 4 times the Laplace transform of t cubed. Now let's identify things here. From what I've written here, let me use green. Our a in the cos is 2, and our n in power t is 3. And we know for t power n, we have n factorial over s power n plus 1. And again, we are aware that for cos at, it is s over s squared plus a squared. We know our a, we'll just substitute. We know our n, we'll just substitute. So let's substitute and see. We are now going to have our f of s will be equals to 5 dot, our A is 2. So the whole of this, we are going to bring this, which is S over, our A is 2, so it will be S squared plus 2 squared. Then minus 4. I think I needed to work this out before I have the final thing. So we are going to have 5 dot, cos 2t is S over S squared plus A, but A is 2 squared, then minus 4. For t cube, our n is 3 factorial, divided by S into 3 plus 1. Now you have 5s over S squared plus 4 minus 3 factorial is just 3 factorial is just 3 times 2 times 1, which is just 6. So we have 6 here. Now 6 times 4, 24. So it means we have 24 over S power 4. So our Laplace transform f of S will be 5s over S squared plus 4 minus 24 over S power 4. So that marks the end of revision 1. It was not easy at the beginning to get our table, but you don't need to go through all this. You just need to remember. If you can remember this, then you can work out these problems without any problem. All right.